So having something like this from the homework, I also think you should check on, I think I've done a lot of these problems too. There's a video also on there. But the biggest thing for this one is we have a secondary electrophile. So that tells me SN1 or SN2. So I haven't narrowed it down. I look at my nuke and I see that it's reactive and small. How do I know that? Because this is Na plus, Cn minus. So this is a carbon triple bond to a nitrogen with a lone pair, right? And the solvent here is a protic. So that's also telling me SN2, SN2, right? So it seems like SN2. So that means I need to think about inversion. I need to think about where the leaving group's at, the carbon that's attached to. So in this case, sigma star, if the bond is here, sigma star, right? The antibonding orbital is over there. So I can take the carbon, needs to come to 180 degrees away, breaks the carbon-bromine bond. Now, what doesn't need to change is the wedges and dashes in this case, because the leaving group wasn't on a wedge or dash. But this carbon right here kind of gets pushed over because this had to come from the opposite side. All right, so the bromine is pointed to the right, the nucleophile need to be pointed to the left. So in this case, it would be C, N, and then the other thing we made was Br minus. So then you got to figure out, is it R or S? Well, we'll do one. I'll do the starting material. So this is green. This one's H is green. Bromine's going to be red. It's going to be white. It's going to be blue. Red, white, blue. Red, white, blue. This is S to start, which means at the end it should turn to R. And it does. So you got to be able to do your, that's like the old school, do your rankings for R and S. You can still, if I have something like that, you can still use your model kit. Okay, so this is 28. We need to decide how do we make this from a nucleophile and electrophile via an SN2 reaction. So basically we need to look, this is tough because we got to look at where the bonds can be formed. So it's really either one of these two sides. It's either this side or this side, right? So the oxygen is going to be our nucleophile. So either we could make it from something that looked like, maybe put a leaving group here, plus O minus, that could be one version. Another version could be, let's see, we'd have the oxygen on this side with an O minus, plus the bromine, right, on that alkyl halide. So the hard part is to look at where, like, to make these disconnections, to realize, oh, these are the parts I need to, like, look at. And the reason I know those are the parts because you look for the polar bonds. So oxygen, carbon. So I break it this way. I have a bromine here on an sp2 hybridized carbon. And I have a small reactive nucleophile. But you've never seen me do anything with this, right? If you notice, all the electrophiles we've used have all been sp3 hybridized. So this actually won't be a good method to do this. So it actually has to be this way. Where you have a primary alkyl halide, like a small electrophile, right? We've never seen an electrophile like this. And then this could react into an SN2 type reaction. All right, so again, here's the reaction. They want us to draw the major organic reaction, right? So these are tough questions, right? These are tougher questions than maybe I almost even ask you on a test or exam. But they're good practice because they're tough. So again, let's look at our electrophile. What kind of electrophile do we have? Hopefully you see we have a secondary electrophile. So that could be SN1 or SN2. So that doesn't limit anything. We're going to look at the nucleophile. And I guess the nucleophile is water is on top there. I would definitely call that unreactive. Right? Water's not reactive. So that makes me think SN1, right? And then I look at the solvent. What kind of solvent do we have? It's protic. Right? So that makes me think SN1. SN1. So it seems like it's going to be SN1. Right? Okay, so it's SN1. So what does that mean? That means, right, we could have carbocations, which means we could have rearrangements. So here in this first step, if you're looking at this, like, well, what's going to happen in an SN1 reaction? We just said water is unreactive. So the first thing that's going to happen is actually the leaving group is just going to leave. Leaving group leaves. Okay, what does that give us? Oops, that's silly. What does that give us? So the carbocation there, right? All right, but then that's a secondary carbocation. So we all know carbocations can rearrange. So we want to look for those sigma bonds 2 bonds away, especially with things with more carbons on them. So what can happen actually is there's going to be a rearrangement. So the hydrogen is going to move over. Not the carbon, the hydrogen. Because if the carbon moved over, it'll also be a secondary. But if the hydrogen moves over, rearrange. It's the old H shift. We went from a secondary carbocation to now having a tertiary carbocation, which is more stable. Okay? Can we make it more stable than this? The only way I can make it more stable is a benzylic or a allylic, and I don't see any pi bonds. So now it seems like it's time for the nucleophile to step in. So water is going to add. Right? So nuke adds. What's that going to give us? Water, the oxygen is still attached to those two H's, so don't try to cheat yourself. These steps. All right? So the last thing that's going to happen is we're actually going to have proton transfer. All right? And the final product would be the alcohol. Now, it doesn't matter in this case, but when this solvent adds right here, you could add from the top or the bottom, right? So you could put the wedges and dashes. In this case, it doesn't matter because this is an asymmetric center, but you could imagine it would. You'd form both products, right? Carbocations you could attack from both the top or the bottom when those add in. So the conjugate base of this would be this reacting with a base. So if there's a base floating around as a lone pair, right, that means this needs to be an acid. So where is this going to react? So if it's a base, it's going to take the polar bond to hydrogen. So it's going to give you the base, not the plus charge B, whatever that is, could be anything. And then your conjugate base would be this. So this would be your conjugate base. Right? So they ask for a conjugate acid, or if they ask for a conjugate base, pretend whatever you have is reacting with a base. Right? If they ask for a conjugate acid, pretend whatever you have is reacting with an acid. Right? So it's like the other side of the arrow. That's all it is. Does that make sense?